Pierre-Simon Marquis de Laplace was an influential French scholar whose work was important to the development of mathematics, statistics, physics, and astronomy. He summarized and extended the work of his predecessors in his 5-volume Mécanique céleste. This work translated the geometric study of classical mechanics to one based on calculus, opening up a broader range of problems. In statistics, the Bayesian interpretation of probability was developed mainly by Laplace. Laplace formulated Laplace's equation, and pioneered the Laplace transform, which appears in many branches of mathematical physics, a field that he took a leading role in forming. The Laplacian differential operator, widely used in mathematics, is also named after him. He restated and developed the nebula hypothesis of the origin of the solar system and was one of the first scientists to postulate the existence of black holes and the notion of gravitational collapse. Laplace is remembered as one of the greatest scientists of all time, sometimes referred to as the French Newton or Newton of France. He possessed a phenomenal natural mathematical faculty superior to that of any of his contemporaries. Laplace became a Count of the First French Empire in 1806 and was named a Marquis in 1817, after the Bourbon Restoration. Early years. The original documents relating to the life of Laplace were lost when the family chateau of Saint-Julien de Malic, near Lisieux, the home of his great-great-grandson, the Comte de Colbert Laplace, burned in 1925, and some had been destroyed earlier. When his house at Arcueil near Paris was looted by housebreakers in 1871. Laplace was born in Beaumont-en-Auge, Normandy on 23 March 1749 at Beaumont-en-Auge, a village 4 miles west of Pont-l'Evêque in Normandy. According to W. Rousball, his father, Pierre de Laplace, owned and farmed the small estates of Marquis. His great-uncle, Maître Oliver de Laplace, had held the title of Chirurgien Royal. It would seem that from a pupil he became an usher in the school at Beaumont, but, having procured a letter of introduction to D'Alembert, he went to Paris to advance his fortune. However, Karl Pearson is scathing about the inaccuracies in Rousball's account and states, indeed, Caen was probably in Laplace's day the most intellectually active of all the towns of Normandy. It was here that Laplace was educated and was provisionally a professor. It was here he wrote his first paper, published in the Mélanges of the Royal Society of Turin, Tome IV. 1766 to 1769, at least 2 years before he went at 22 or 23 to Paris in 1771. Thus, before he was 20 he was in touch with Lagrange in Turin. He did not go to Paris, a raw, self-taught country lad with only a peasant background. In 1765, at the age of 16, Laplace left the school of the Duke of Orleans, in Beaumont, and went to the University of Caen, where he appears to have studied for 5 years. The École Militaire of Beaumont did not replace the old school until 1776. His parents were from comfortable families. His father was Pierre Laplace, and his mother was Marie-Anne Sauchon. The Laplace family was involved in agriculture until at least 1750, but Pierre Laplace was also a cider merchant and syndic of the town of Beaumont. Pierre-Simon Laplace attended a school in the village run at a Benedictine priory, his father intending that he be ordained in the Roman Catholic Church. At 16, to further his father's intention, he was sent to the University of Caen to read theology. At the university, he was mentored by 2 enthusiastic teachers of mathematics, Christophe Gadbled and Pierre Lecanou, who awoke his zeal for the subject. Here Laplace's brilliance as a mathematician was quickly recognized, and while still at Caen he wrote a memoir sur le calcul intégral aux différences infiniment petites et aux différences finies. This provided the first intercourse between Laplace and Lagrange for Lagrange, who was the senior by 13 years, had recently founded in his native city of Turin a journal named Miscellanea Turinensia, in which many of his other early works were printed, and it was in the fourth volume of this series that Laplace's paper appeared. About this time, recognizing that he had no vocation for the priesthood, he determined to become a professional mathematician. In this connection, reference may perhaps be made to the statement, which has appeared in some notices of him, that he broke altogether with the Church and became an atheist. Laplace did not graduate in theology but left for Paris with a letter of introduction from Lecamus to Jean-Laurent D'Alembert, who at that time was supreme in scientific circles. According to his great-great-grandson, D'Alembert received him rather poorly, and to get rid of him gave him a thick mathematics book, saying to come back when he had read it. When Laplace came back a few days later, D'Alembert was even less friendly and did not hide his opinion that it was impossible that Laplace could have read and understood the book. But upon questioning him, he realized that it was true, and from that time he took Laplace under his care. Another version is that Laplace solved overnight a problem that D'Alembert set him for submission the following week, then solved a harder problem the following night. D'Alembert was impressed and recommended him for a teaching place in the École Militaire. With a secure income and undemanding teaching, Laplace now threw himself into original research, and in the next 17 years, 1771 to 1787, he produced much of his original work in astronomy. Laplace further impressed the Marquis de Condorcet, and already in 1771 Laplace felt that he was entitled to membership of the French Academy of Sciences. However, in that year, admission went to Alexandre Théophile Vandemondon in 1772 to Jacques-Antoine Joseph Cousin. Laplace was disgruntled, and at the beginning of 1773, D'Alembert wrote to Lagrange in Berlin to ask if a position could be found for Laplace there. However, Condorcet became permanent secretary of the Academy in February, and Laplace was elected associate member on the 31st of March, at age 24. On the 15th of March 1788, at the age of 39, Laplace married Marie Charlotte de Courty de Romanges, a pretty 18-and-a-half-year-old girl from a good family in Besançon. The wedding was celebrated at Saint Sulpice, Paris. The couple had a son, Charles-Émile, and a daughter, Sophie Suzanne. Analysis, probability and astronomical stability. Laplace's early published work in 1771 started with differential equations and finite differences, but he was already starting to think about the mathematical and philosophical concepts of probability and statistics. However, before his election to the Academy in 1773, he had already drafted two papers that would establish his reputation. The first, Mémoire sur la probabilité des causes par les événements, was ultimately published in 1774, while the second paper, published in 1776, further elaborated his statistical thinking and also began his systematic work on celestial mechanics and the stability of the solar system. The two disciplines would always be interlinked in his mind. Laplace took probability as an instrument for repairing defects in knowledge. Laplace's work on probability and statistics is discussed below, with his mature work on the analytic theory of probabilities. Stability of the solar system. Sir Isaac Newton had published his Philosophiae Naturalis Principia Mathematica in 1687, in which he gave a derivation of Kepler's laws, which described the motion of the planets, from his laws of motion and his law of universal gravitation. However, though Newton had privately developed the methods of calculus, all his published work used cumbersome geometric reasoning, unsuitable to account for the more subtle higher-order effects of interactions between the planets. Newton himself had doubted the possibility of a mathematical solution to the whole, even concluding that periodic divine intervention was necessary to guarantee the stability of the solar system. Dispensing with the hypothesis of divine intervention would be a major activity of Laplace's scientific life. It is now generally regarded that Laplace's methods on their own, though vital to the development of the theory, are not sufficiently precise to demonstrate the stability of the solar system, and indeed, the solar system is understood to be chaotic, although it happens to be fairly stable. One particular problem from observational astronomy was the apparent instability whereby Jupiter's orbit appeared to be shrinking while that of Saturn was expanding. The problem had been tackled by Leonhard Euler in 1748 and Joseph Louis Lagrange in 1763, but without success. In 1776, Laplace published a memoir in which he first explored the possible influences of a purported luminiferous ether or of a law of gravitation that did not act instantaneously. He ultimately returned to an intellectual investment in Newtonian gravity. Euler and Lagrange had made a practical approximation by ignoring small terms in the equations of motion. Laplace noted that though the terms themselves were small, when integrated over time they could become important. Laplace carried his analysis into the higher-order terms, up to and including the cubic. Using this more exact analysis, Laplace concluded that any two planets and the Sun must be in mutual equilibrium and thereby launched his work on the stability of the solar system. Gerald James Whitrow described the achievement as the most important advance in physical astronomy since Newton. Laplace had a wide knowledge of all sciences and dominated all discussions in the academy. Laplace seems to have regarded analysis merely as a means of attacking physical problems, though the ability with which he invented the necessary analysis is almost phenomenal. As long as his results were true, he took but little trouble to explain the steps by which he arrived at them. He never studied elegance or symmetry in his processes, and it was sufficient for him if he could by any means solve the particular question he was discussing. On the figure of the Earth, during the years 1784 to 1787, he published some memoirs of exceptional power. Prominent among these is one read in 1783, reprinted as Part 2 of Théorie du mouvement et de la figure elliptique des planètes in 1784, and in the third volume of the Mécanique céleste. In this work, Laplace completely determined the attraction of a spheroid on a particle outside it. This is memorable for the introduction into analysis of spherical harmonics or Laplace's coefficients, and also for the development of the use of what we would now call the gravitational potential in celestial mechanics. Spherical Harmonics in 1783, in a paper sent to the Académie, Adrien-Marie Legendre had introduced what are now known as associated Legendre functions. If 2 points in a plane have polar coordinates and where r, then, by elementary manipulation, the reciprocal of the distance between the points, d, can be written as. This expression can be expanded in powers of r, using Newton's generalized binomial theorem to give the sequence of functions P0k as the set of so-called associated Legendre functions, and their usefulness arises from the fact that every function of the points on a circle can be expanded as a series of them. Laplace, with scant regard for credit to Legendre, made the non-trivial extension of the result to 3 dimensions to yield a more general set of functions, the spherical harmonics or Laplace coefficients. The latter term is not in common use now. Potential theory. This paper is also remarkable for the development of the idea of the scalar potential. The gravitational force acting on a body is, in modern language, a vector, having magnitude and direction. A potential function is a scalar function that defines how the vectors will behave. A scalar function is computationally and conceptually easier to deal with than a vector function. Alexis Clairaut had first suggested the idea in 1743 while working on a similar problem, though he was using Newtonian-type geometric reasoning. Laplace described Clairaut's work as being in the class of the most beautiful mathematical productions. However, Rousball alleges that the idea was appropriated from Joseph Louis Lagrange, who had used it in his memoirs of 1773, 1777 and 1780. The term potential itself was due to Daniel Bernoulli, who introduced it in his 1738 memoir Hydrodynamica. However, according to Rouse Ball, the term potential function was not actually used until George Green's 1828 an essay on the application of mathematical analysis to the theories of electricity and magnetism. Laplace applied the language of calculus to the potential function and showed that it always satisfies the differential equation. An analogous result for the velocity potential of a fluid had been obtained some years previously by Leonhard Euler. Laplace's subsequent work on gravitational attraction was based on this result. The quantity 2V has been termed the concentration of V, and its value at any point indicates the excess of the value of either over its mean value, in the neighborhood of the point. Laplace's equation, a special case of Poisson's equation, appears ubiquitously in mathematical physics. The concept of a potential occurs in fluid dynamics, electromagnetism and other areas. Rouse Ball speculated that it might be seen as the outward sign of one of the a priori forms in Kant's theory of perception. The spherical harmonics turn out to be critical to practical solutions of Laplace's equation. Laplace's equation in spherical coordinates, such as are used for mapping the sky, can be simplified using the method of separation of variables into a radial part, depending solely on distance from the center point, and an angular or spherical part. The solution to the spherical part of the equation can be expressed as a series of Laplace's spherical harmonics, simplifying practical computation. Planetary and lunar inequalities. Jupiter-Saturn Great Inequality. Laplace presented a memoir on planetary inequalities in 3 sections, in 1784, 1785, and 1786. This dealt mainly with the identification and explanation of the perturbations now known as the Great Jupiter-Saturn Inequality. Laplace solved a long-standing problem in the study and prediction of the movements of these planets. He showed by general considerations, first, that the mutual action of 2 planets could never cause large changes in the eccentricities and inclinations of their orbits, but then, even more importantly, that peculiarities arose in the Jupiter-Saturn system because of the near approach to commensurability of the mean motions of Jupiter and Saturn. In this context, commensurability means that the ratio of the 2 planets' mean motions is very nearly equal to a ratio between a pair of small whole numbers. 2 periods of Saturn's orbit around the Sun almost equal 5 of Jupiter's. The corresponding difference between multiples of the mean motions corresponds to a period of nearly 900 years, and it occurs as a small divisor in the integration of a very small perturbing force with this same period. As a result, the integrated perturbations with this period are disproportionately large, about 0.8 degrees of arc in orbital longitude for Saturn and about 0.3 degrees for Jupiter. Further developments of these theorems on planetary motion were given in his 2 memoirs of 1788 and 1789, but with the aid of Laplace's discoveries, the tables of the motions of Jupiter and Saturn could at last be made much more accurate. It was on the basis of Laplace's theory that Delambre computed his astronomical tables. Celestial mechanics. Laplace now set to himself the task to write a work which should offer a complete solution of the great mechanical problem presented by the solar system, and bring theory to coincide so closely with observation that empirical equations should no longer find a place in astronomical tables. The result is embodied in the Exposition du Système du Monde and the Mécanique céleste. The former was published in 1796, and gives a general explanation of the phenomena, but omits all details. It contains a summary of the history of astronomy. This summary procured for its author the honor of admission to the 40 of the French Academy and is commonly esteemed one of the masterpieces of French literature, though it is not altogether reliable for the later periods of which it treats. Laplace developed the nebula hypothesis of the formation of the Solar System, first suggested by Emanuel Swedenborg and expanded by Immanuel Kant, a hypothesis that continues to dominate accounts of the origin of planetary systems. According to Laplace's description of the hypothesis, the Solar System had evolved from a globular mass of incandescent gas rotating around an axis through its center of mass. As it cooled, this mass contracted, and successive rings broke off from its outer edge. These rings in their turn cooled, and finally condensed into the planets, while the Sun represented the central core which was still left. On this view, Laplace predicted that the more distant planets would be older than those nearer the Sun. As mentioned, the idea of the nebula hypothesis had been outlined by Immanuel Kant in 1755, and he had also suggested meteoric aggregations and tidal friction as causes affecting the formation of the Solar System. Laplace was probably aware of this, but, like many writers of his time, he generally did not reference the work of others. Laplace's analytical discussion of the Solar System is given in his Mécanique céleste, published in 5 volumes. The first 2 volumes, published in 1799, contain methods for calculating the motions of the planets, determining their figures, and resolving tidal problems. The third and fourth volumes, published in 1802 and 1805, contain applications of these methods, and several astronomical tables. The fifth volume, published in 1825, is mainly historical, but it gives as appendices the results of Laplace's latest researches. Laplace's own investigations embodied in it are so numerous and valuable that it is regrettable to have to add that many results are appropriated from other writers with scanty or no acknowledgement, and the conclusions, which have been described as the organized result of a century of patient toil, are frequently mentioned as if they were due to Laplace. Jean-Baptiste Paulin, who assisted Laplace in revising it for the press, says that Laplace himself was frequently unable to recover the details in the chain of reasoning, and, if satisfied that the conclusions were correct, he was content to insert the constantly recurring formula, il est ainsi que tout voir que. The Mécanique céleste is not only the translation of Newton's Principia into the language of the differential calculus, but it completes parts of which Newton had been unable to fill in the details. The work was carried forward in a more finely tuned form in Félix T. Serran's Traité de mécanique céleste, but Laplace's treatise will always remain a standard authority. Black holes. Laplace also came close to propounding the concept of the black hole. He suggested that there could be massive stars whose gravity is so great that not even light could escape from their surface.